We have a couple other things to talk about. One is this idea of the common ion effect. So let's imagine we're looking at a solution of our mercury chloride, for example. We'll just stick with this same salt, right? And we want to know, what's going to, we want to understand the equilibrium here, right, or KSP. But let's imagine we have this mercury chloride solution, and we've already calculated at room temperature with KSP given. We will see a certain concentration of mercury. We calculated a couple videos ago. In fact, I think I have the answer just sitting over here. Yeah, our mercury concentration will be 6.7 times 10 to the minus 7 molar. So that would be what we'd expect if we just put this in solution. But what if we have this, instead of just being in water, we instead have it in a solution of sodium chloride? Say we have a 0.1 molar solution of sodium chloride. I want you to pause the video and think, will we have a higher concentration of mercury, the same concentration of mercury, or a lower concentration of mercury in this solution than we did for just the mercury chloride salt in pure water without any sodium chloride present? Okay, hopefully you paused the video, took a chance to think about that. The answer to this question is that the solubility will be lower. So we'll have a lower concentration of mercury in this case. Now, why is that? And the answer has to do with the fact that this is sodium chloride. So we already have chloride ions present in solution. An equilibrium doesn't care where your ions come from, it just cares about the concentration that's present in your solution. So if we calculate KSP here, and we want to find the concentration of our mercury, we know that KSP is this value that I just wrote, but it is also, this product of our concentrations here. Now, we already have chloride present. And what we can do is we can plug in the value of 0.1 molar that we already know is present for our chloride. All right, so that will leave X here, and we can solve for this X, and we're going to get a very small number. So X will be equal to 0.1 squared. 0.1 squared is, so X will be equal to 1.2 times 10 to the minus 18 divided by 0.1 squared. Let's again enter that into the calculator. 1.2 times 10 to the minus 18 divided by 0.1 squared. 1.2 times 10 to the minus 16. So we can see that's a much, much lower concentration of mercury than what we had when we just had pure water. Our concentration was 10 to the minus 7. 7 times 10 to the minus 7, and now it has decreased to 1 times 10 to the minus 16. That's like 9 orders of magnitude. That's a huge difference. Basically, there's no mercury that's going to be present, and this is due to the fact that we have a shared ion here, right? The fact that there's already chloride present in solution prevents that mercury from being released from the salt because there's already chloride there. And so mathematically, we can see that working out here, and just conceptually as well. So this common ion effect is an important effect in terms of solubility. If we have ions present from other salts or other things that are already in our solution, it will affect all the equilibria happening in that solution. So it will affect the solubility of salts that are present.